Can you predict what happens when a particle reflects off an impenetrable wall in a potential well? Find out the answer and more in today's quantum puzzle. And this is problem 10.5. A particle of mass m and energy E is incident from the left on the potential V of x, which is 0 for less than a, negative V naught for negative a to 0, and infinity for anything greater than 0. Part A. If the incoming wave is AIKX, and be aware that this is incoming and the sign on the exponential, where K is our normal constant, and find the reflected wave. Then he gives the answer. Part B. Confirm that the reflected wave has the same amplitude as the incident wave. This is a really important result, so keep that in mind. And then C. Find the phase shift from equation 10.40 for a very deep well, i.e. E much less than V naught, and gives the answer. Okay, so the reason why we're covering this question is it actually gives us quite a lot to think about. Why do we care? Well, in this formulation, instead of dealing with partial wave analysis via the amplitudes, this offers a way to quantify how wave functions are altered when interacting with potentials, and that's very different from what we had seen previously. So this will be really cool. The challenge for you is why does this work without the amplitude that we need to measure? And again, this is mainly targeting on part B. And why is it that the partial amplitudes that we saw from the wave analysis or partial wave analysis in the last section is no longer as needed for this regime? So think about that. And then, of course, comment for the PDF, and I will send that link to you, or you can just go straight to the Patreon page. I guess I have too many links in the description, and sometimes it's being weird. And if you're curious about the world of science, be sure to subscribe. I post educational content every week to quench your thirst for curiosity. So with this, let's dive into this question. All right, stop number one. Before we can do anything, we need to analyze the Schrödinger equation within each region defined by the piecewise potential function to determine the appropriate types of solutions for each case. And as we see here, the green line just tells us that that was 0 for x less than the a point here. And then we had negative v naught from negative a to 0, and then we had infinity here at 0. So this tells us that we can't do much about this. This is an impenetrable wall, all things considered, and we have to look at what type of solutions are allowed. Now, we've seen what happens with wells, and we've seen what happens with free particles, so keep those both in mind as we solve the differential equation. So, that brings us straight to, well, analyze the time-independent Schrödinger equation within each region, and we know that for x less than negative a, the potential is 0, so that part of the equation goes away. We simply maneuver this over to the right-hand side, so multiply by 2m, divide by negative h bar, and that's what we get here. That leads us straight to our K substitution that we've seen plenty of times by now. If you need a refresher, chapter 2 would be the go-to. And we saw that because the potential is 0 here, there's nothing to do to interfere with the waves, so what we see here are exponentials. And of course, you could have exponentials that look like this, or equivalently, you could have sine and cosine, but here they represent slightly different things. So as a reminder, exponentials are inherent with traveling waves. Think about the free particle we covered back in chapter 2. This is what the solution needs to be the form of. Now, for the region where we have negative a to 0, where we have the well, we clearly have a potential that is non-zero, so that would go to V naught. And we have to do the same thing here. Get everything, get this, well, that's supposed to be a square, excuse me. That's supposed to be a square too. Go ahead and write that in. Can't believe I didn't catch that in editing. 2, supposed to be a square derivative. My bad. But we need to isolate this square derivative and then solve it away. So we do that, we add the potential term over, factor the wave function out, we're good to go. We get E plus V naught instead of the traditional minus V naught. That's why we kind of orient it this way. Then, of course, if we divide over the constants, again, it's supposed to be a square. Can't believe I missed that. And then we see here that we can just make a new substitution with the E plus V naught instead of just E as K prime. And we see that the solutions come here in the form of sine and cosine. okay? And so we can see that the full solution set is this for each interacting region, okay? And as a reminder, if exponentials are traveling waves, the trigs represent standing waves, and that's what we expect to see. To the left of negative a, we see we have a free particle in terms of the solutions and the equations. Here we have a well that is a standing wave, and as you know from infinite square well back in chapter 2, we see that this needs to happen inside a well. And so one of the immediate consequences of this right boundary term here at 0 is that clearly we saw that we needed to get a solution to where that wave function goes to 0 at the infinite boundary. So this tells us that the translation for the boundary condition is that psi of 0 equals 0. And that's what we see summarized here. And again, standing waves in the infinite square well, we've seen that before. So none of this is necessarily new, but it's good to reinforce it. So if we plug in 0, we see that sine of 0 goes to 0, so that whole term goes away. But cosine of 0 goes to 1, thus leaving us only d, the coefficient d. But since the whole thing has to equal 0, this highlights that d equals 0 immediately. So now the task is to solve for a, b, and c. But really, since all we wanted was the reflected wave, we really have to highlight b here. Okay, that's really what we want. And we were told that this is the incoming wave, so this has to be the reflected wave, and thus B is the highlight. So let's get into how to do that. All right, so as just mentioned, we still need to find B from the boundary conditions on the left boundary. And these tell us that we need to have the continuity of the wave function at negative A and its derivative at negative A. So with this, we see that the function at negative A, the negative A just gives us that. We'll have to travel through. The negative cancels, and then we just plug in negative a to the sine. Since d equals 0, we don't have to worry about the cosine, which is in agreement with what we saw for the infinite square well solutions and finite square well solutions. But since sine is an odd function, the negative can move through. No negatives up here because they cancel, and then we have a negative here. Cool. Now the derivative evaluated at negative a, pretty much the same thing except we have some constants out front now. And so what we see here is that cosine, being an even function, gets rid of the negative inside, and we see that we have pretty much everything alike. So we're pretty good to go now. But we still have three unknowns in A, B, and C, but we can eliminate one of the unknowns by taking the continuity of the derivative equation and dividing it by the continuity of the wave function equation, and that can eliminate C right off the bat. And that's what we see here. So stacking them in that ratio, we get C and C divide, and then we see that we're just left with A and B functions over here on the left-hand side, and no constants, but a weird trig function cotangent on the right-hand side. So what we need to do now that we've eliminated C is multiply this denominator over to the cotangent, and of course we see that that's distributed down here. Please go reference the PDF if you want every excruciating step-by-step part of it, because that will help you if you need it. But more importantly, we see that this is just a game of algebra. We really only need to solve for B, because if we want to solve for A, we can via normalization, but we really don't want to. What we really want to do is highlight B, so that's why we're color coordinated A and A, B and B, and then we could algebraically solve and get A's to one side, B on the other, and let's get to that result. All right, so as promised, we have A's on one side, B's on the other, and we see that we can factor out conveniently A and a negative exponential, B and a positive exponential. So we do that. Divide over to isolate B. We're good to go. Go ahead and simplify that. That turns this -1 into a -2. So we're good to go. And as a result, we can write down the full wave function. And this is the entire wave function for the region, anything to the left of negative A. However, we were asked for the reflected wave, and based on the sign of the exponents, we know that the reflected wave has to be the negative sign. So that's going to be this side here, okay? And so we know that this is the incoming, this has to be the reflected, so we say that the reflected wave function is as such. And that wasn't too bad. Again, if we want to find A, all we have to do is normalize this wave function. That gives us everything we need to know. So at this point in the problem, if you're finding this helpful, please don't forget to give it a thumbs up. It helps more curious minds like yours discover this content and helps the channel grow. But with this, let's head to stop number 2 and check the amplitudes. Okay, so as promised, step number 2, we need to confirm that both the incident and the reflected waves have the same amplitude, and we need the squared magnitudes to be equal due to conservation of probability. Thus, we need to show that b magnitude squared equals a magnitude squared. And since the magnitude squared is b star b, we simply need the complex conjugate of b and multiply that by b. After we take that, we see that this goes to positive, negative, negative, positive, and that's what we see indicated here. We get a star a, we can group that together. The positive exponential here cancels with the negative one here, as indicated with that cancel sign. Switch the signs here, multiply it by the unswitched signs there on the complex conjugate. This turns this exponential to a positive, and then when you join that with the negative exponential, that one cancels as well. No big deal. Here's where the algebra gets a little messy, but it's pretty straightforward. We need to distribute this numerator to numerator, denominator to denominator. And when we do that, we see that the cross terms here in both the numerator and denominator cancel. Now, because we have a negative here and a negative here, that turns this to a positive on the boundaries or on the edges. So that's pretty cool. And then after that, after we cancel these cross terms, what we see is that the numerator is equal to the denominator, so they cancel out to 1, and thus leaving us with a squared. So this shows us that the amplitudes are the same, and thankfully the conservation of probability plays a big role in that. Now, if you remember back to the challenge question, this is why the amplitudes in general don't matter, but this says nothing about the phase. Okay, clearly the reflected wave is probably not going to be in phase with the incident wave, and that's why we want to solve for the phase shift. That's why this method is so cool and why it works. And it's a lot easier, all things considered, which we'll see in the next question when we compare the two methods head on head. So, with that, let's get to step number 3 and wrap this problem up. All right. So if we wish to find the phase shift delta, we simply need to compare forms with the equation 10.40. And as that's what we see here. Nothing too bad, but we see we have a lot of exponentials, one with the incident wave, one with the reflected wave. Although it's kind of hidden in here, the negative kx tells you the direction, and that goes to the left, so we're good to go. Now comparing the solutions to the left side of A and to the right side, we see here that we have the constant A and the constant A that cancel, which is why, again, we didn't solve for it. We don't need to, but we could have if we wanted to normalize. Good to go. After we get rid of that normalization constant, what we see is that the incident waves on both sides cancel, which is awesome. We don't like that. We don't want them. But we see that this exponential, we can distribute the I in it. We do that here, and then we could split them up here. What that allows us to do is after we cancel the incident waves, we can also eliminate the reflected wave parts and just focus on the phase shift factor. And that is what we want to do now. All right, so get that negative over there, take the log of both sides to isolate delta, and then this delta term can be isolated holistically by dividing by 2i, and that we see is the actual answer. And in this case, this is the exact answer, but of course, we can approximate the solution based on the scenario for a very deep well, i.e., E much less than V0. In this situation, we know that if we have the 2ME here, because E is so much less than V0, we know that the constants don't matter, and this V0 term here makes this fraction much bigger. What it translates to is that K is much less than K prime. And what that's going to do is allow us to simplify this down really cleverly, and we'll just say, and then in the next slide we'll see how it does that. But be aware, these are the ramifications of all the approximations, especially what we saw in the low energy scattering. These approximations make our life easy. Just know how to apply them and take your time with where they come from. So, with that, this accounts or amounts to the factor k being negligible, so we could say something like k equals 0 in comparison, and thus, when we do that, this term and this term cancel out quickly. And then that leaves us with the numerator with a common factor in the denominator, only leaving us with the -1. So cancel, cancel, -1 and the negative out front cancel, so we don't have to worry about anything to do with the logs and their domain restrictions. And then we see that the log is the inverse function of the exponential, so that cancels with that, Cool. Then we get the 2i out front and the 2i inside canceling. Beautiful. And that leaves us with negative Ka. So we successfully showed that the phase shift was just a negative Ka. And what did we know about the Ka from other parts of this problem, but that it was, in the low energy case, much less than 1. So this is really cool to see that the Ka keeps coming back and the wave number K keeps popping up with the incident of the width of the well. So all of this is making physical sense, but as you see, nothing of the math was too bad here, all things considered, especially when compared to the partial wave amplitudes and all the spherical Hankel, Bessel, and all the Legendre polynomials trying to get them together. So very cool method to use, very impactful. So keep that in mind as you're practicing problems. Awesome. Well, thank you for watching, and if you've gotten this far, share this with a friend who's also curious about science, and let's grow this learning community together. In summary, you now know a lot about what's going on with both regimes, both the partial wave analysis and the phase shift analysis. Both are powerful, but we still have an even more powerful method coming up with the Born approximation. So be aware and pay attention to when the videos come out, because that will be something that you use in several classes. And if you've had E&M before, you've probably seen some of this analysis stuff before. Scattering is a big theory in physics altogether, especially because that's what experimentalists need in all their experiments. I mean, think about CERN. It's nothing but scattering problems, colliding two particles or accelerating them. It's actually a really useful thing and really important. Unfortunately, the math behind it is not nice, so you have to be aware of that. But nonetheless, uh, this is also going to come up again, and uh, believe I believe it's going to be in classical mechanics in that book too. They talk about it, so it'll be around in us, and then we'll see how 3 different observation points of it will happen: classical mechanics, E&M, and the quantum world, and it'll all fuse together when we get to the field theory. So that'll be really fun. But that being said, thank you again to all the supporters of this channel. You make this possible. Welcome to the family, Nathan. I appreciate your contributions, and I look forward to seeing what your nerd brain likes to talk about. It'll be a real fun, especially with the new semester. Already getting a lot of DMs on Instagram about the different classes, so I'll be looking forward to keeping up with everybody on that. Again, linear algebra, always a good go-to. Keep that one in mind as you're dealing with all your classes, because it comes up again and again and again. That being said, books, notes, and other reference materials are found below or on the Patreon page with the PDFs. I like to reference them out because more than one perspective is generally needed. So, whatever your learning style is, let's talk, let's communicate, let's see what we can do to better this effort to broaden education and better it, because there's a lot of resources now and everyone has a different way of learning. So keep that in mind. If you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.